So the zeros depend on where you feed the input and where you take the output from. Let me not add this part. And the poles depend on the loop itself. Okay, not really the location of the input or the output. When I say loop, essentially it's the loop gain, right? So if you have a given loop gain, you will have a given denominator polynomial, which is related to 1 by 1 plus 1 over L of S. Okay. And zeros depend on the location of the input and the output. Okay. Now, of course, because you can manipulate the zeros, you can also come up with pole zero cancellation sometimes. But you can't just change the poles by applying inputs to different points or taking output from different points without changing the loop itself. Okay. So these are properties of feedback system. Now this also can be used in design. So if you find that your poles are at too low frequencies or they are imaginary and they are ringing, I mean you have ringing in the response, you will have to change the loop in some way. Okay, that's a prerequisite. Or let's say you want to modify the transfer function by changing the zeros, then you can try to look for other locations where you can inject the signal or where you can take the signal out of and then manipulate the zeros of the transfer function. Okay. And for a stable feedback system, the loop gain L of S should have a predominantly first order behavior. Okay. So ideally I would like the loop gain to do this, okay, meaning it is just an integrator, it has infinite DC gain and it has a 20 dB per decade roll off throughout. It has a certain unity gain frequency which I denote by omega u loop. Okay. This is the magnitude of the loop gain. Now in reality I do know that I will have a finite DC gain, okay, and also I will have parasitic poles, and for stability I should place these parasitic poles and zeros well beyond the unity gain frequency. Okay. Now we have a finite DC gain and a certain unity loop gain frequency. So accuracy depends on the DC loop gain. That is, when I say accuracy, what I mean here is you are trying to control something using negative feedback. how accurately it is controlled in steady state depends on the DC loop gain. Okay. And speed depends on omega u loop. That is, if the output is not at the steady state value, the amount of time it takes increases if omega u loop decreases. Okay. To make the circuit respond faster to disturbances, you have to increase the value of omega u loop. Okay. So that's a summary of negative feedback systems. Any questions? So the prototype system we took was this, right? We had an integrator in the forward path. We of course understand that there can be parasitic poles in the forward path as well as the feedback path. But this is the system we started off with. Okay. So to implement this, we need to be able to take the difference between the input and the feedback quantity, and also we need to implement an integrator. Okay. So the feedback part, in case of an amplifier, the feedback part consists of just an attenuator, and we assume that we can realize it using passive components. Okay. Now this part is realized using an op-amp. Okay, the op-amp is designed to realize this part. So it takes the difference between two inputs, and also it has a frequency response that is more or less like that of an integrator. Meaning, if it has to behave like an integrator, it has to have a large DC gain, and also we already saw that for stability, it has to have all its parasitic poles and zeros beyond the unity gain frequency. Okay. So all that is provided by the op-amp. In fact, the op-amp was designed so that you can realize negative feedback systems. Okay. So how would we use it? So for instance, let's take a simple case of an amplifier of gain K. So this is again a very familiar circuit. We have a voltage divider that can implement the feedback path, and we have to take the difference between the input and the feedback quantity, and the integration happens inside the op-amp. Okay. Of course, the op-amp will have an imperfect integrating, it behaves like an imperfect integrator, that is, it has a finite DC gain and also some parasitic poles and zeros. Okay. So this is a prototype circuit, but in general you can use an op-amp to do these things. Okay. That is, you can use an op-amp to realize negative feedback systems. So the job of providing a large loop gain at DC and a first order response is done by the op-amp. Okay. So there are various things that can be called ideal op-amp at the 0th level. An ideal op-amp is something which has infinite gain and infinite unity gain frequency, right? That's what you analyze when you say ideal op-amp circuits. You analyze it by assuming a virtual short between these two. Okay. So an ideal op-amp is defined just by a virtual short between its inputs, and the output can take any value. Okay. Now, for us, when we want to do a little more detailed analysis, what we will assume is that so the next level, we assume an op-amp which has a transfer function of omega u by s. So what at DC the gain is infinity. Okay. So at DC there is indeed a virtual short between the inputs, but as you go to higher frequencies, there is some differential input voltage. The input difference is not zero. Okay. The DC value of the input difference has to be zero in steady state, right? Or rather, when I say DC value, that implies in the long term. Okay. Now, in reality, it's not going to be even this one. So, a real op-amp will have a finite DC gain A0. Okay. And also a second pole and probably a third pole and some zeros and so on. So when we talk about analyzing the circuit with a real op-amp, this is probably the most complicated model we'll use, because beyond this, if you try to do hand calculations, it becomes too complicated. So then we take the help of simulators. Okay. So for us, this is a real op-amp. This is the absolutely ideal op-amp is with a virtual short between its inputs, and you can get various degrees of modeling by using an ideal integrator model, or sometimes you model it just by using the DC gain. You ignore what happens at high frequencies. Okay. So if you put s equal to 0 in this model, you get A0, right? So you use that model also. So I said the real transfer function a real op-amp has a transfer function this, right, which can also be written as okay. So what would be the DC characteristics of this? Now, by the way, I should have defined it earlier. This H of S is the transfer function between the differential input voltage and the output V0. Okay. So H of S is the ratio of the output to the differential input, and that should have this characteristic. Okay. So what will be the DC characteristics of this? If I plot V0 versus VID at DC, what should it be? 20 log 10 A0. V0 versus VID, what will it be? What is it going to be? Ramp. No, this is a DC characteristic. What is the? It's a straight line with a slope of A0, right? Okay, it's a straight line passing through the origin with a slope A0. Is this clear, or does this need further explanation? I am plotting V0 versus VID, not versus time or frequency or anything. Okay. So this ideally this is the DC characteristics. These are the DC characteristics. So what non-idealities may we have here? Saturation. So what does it mean? For small voltage? So it will be fixed at some value. So beyond, the voltage will not increase indefinitely as you increase the input voltage. That is, the range of output voltage is limited to some value. Okay. So in reality, on both sides, it can perhaps be limited. I mean, it will be limited rather. Okay. So the op-amp has two input pins and an output pin, and also it has upper and lower power supplies, right? So what will be the saturation voltages? VDD and VSS. In reality, it will be slightly below VDD and slightly above VSS, but we'll approximate it by assuming that it is VDD and VSS. Okay. In fact, let me not do that right away. So Vmax is less than VDD and Vmin is more than VSS. It is above the bottom rail or below the top rail. It will be limited to that. So many times we do analyze it by assuming that the Vmax equals VDD and Vmin equals VSS. Okay. So these are the DC characteristics. What about the absolute voltage at this point? So far we only talked about VID, that is the difference voltage between the plus and minus input terminals. What will be the voltage at each of these terminals? You have built op-amp circuits, right? Like what is the voltage there at each terminal? What's that? Yeah. It will be 0 volts with respect to ground. Now, what did you say? I didn't hear. Okay, so what is the voltage applied with respect to ground? Huh? Yeah, it can be anything basically, right? So far, we have not even discussed what voltage is going to be at each of these points. So this will be some bias voltage plus, we'll represent it as some bias voltage plus half the differential voltage, and this is some other bias voltage minus, the same bias voltage minus half the differential voltage. Okay. And what are possible values of VCM? Is there some fixed value or can you have any value? What's that? You would like to have it to be? Why? VDD by 2. VDD plus VSS by 2. See, again, VCM has a certain range. This is not something that is fixed. Okay? VCM can be any value in a certain range. Okay? And you can choose the value of VCM with which you can bias the op-amp. Right? It's not that it has to be at the midpoint of the supplies. So, and of course, the range will be contained within VDD and so the range will be somewhere between VDD and VSS, but it's not that the input needs to be biased at the midpoint of the rails. It can be biased anywhere. Okay. So normally, if you say a classical op-amp circuit, what's the value of VDD and VSS and VCM? What's that? Plus or minus? Yeah, or not necessarily. It's plus or minus. This is some positive voltage and this is equal negative voltage below, equal negative voltage with respect to ground. And what is the value of VCM? 0. It's biased with 0 volts. So normally that's how you do things. That if you look at the voltages at the inputs, it will be like this, and this is the ground with which we measure all the voltages. So this will be some supply. Okay. But what I am trying to get at is that it doesn't have to be like this. How would you operate the op amp with a single supply? Now we need two batteries, right? You are familiar with the dual supply. How do you operate it with a single supply? Can you do that? Or do you? Huh? What do you have to do to operate with a single supply? What is the meaning of single supply? So, you have a certain ground and you have just one voltage as supply voltage from that. Okay, not two voltages, that's all. So, all you have to do is to call this the ground. Okay. So, if you shift the ground here, you will also have to shift the input bias. So, in fact, there is absolutely no difference between this and the previous circuit, right? It's only, the only difference is the points that you call ground. Okay. Is this point clear? All we have done is to call a different point as ground. That's all. Okay. Now, as I mentioned earlier, this does not have to be V sub the midpoint of the supplies. It can be some voltage as long as it's in the permissible range. Okay. Now you have changed the circuit a little bit, but as long as you are operating within the range of the op amp, it is fine. The reason I am going through all this is what we will be designing will be single supply. What we use most of the time in a CMOS IC is a single supply. We will not use dual supplies because the single supply already is down to 1.8 volts. It doesn't make any sense to start with 2.9 volt supplies and work with that. Okay. So generally when you design ICs, you refer everything to a single supply. But the difference between single supply and dual supply is only with the location of the ground. Any op amp, even the ones that you buy off the market, can be operated with a single supply, right? Or a dual supply. You just have to bias the input appropriately. That's all. Okay. So the kind of op amps that we will be seeing in this course will have a single supply between the top and bottom rail, and the input will be biased somewhere between the lower and the upper supplies. Okay. Now the range of VCM so one of these two can be equal to the rail. Like for instance, the minimum value can be 0 volts. That depends on the type of op amp. When we design the op amp, we'll see. So the range of the common mode voltages can include 0 volts. In which case it's most convenient because then you don't even have to make an arrangement for biasing the inputs. You can bias it around this one. Okay. So, but for now you just have to keep in mind that we'll operate op amps with a single supply, but it's no different from operating them with a dual supply. You just have to bias the input appropriately. Now, the input has to be biased with a voltage which is within the permissible range. What that permissible range is depends on how you design the op amp. Okay, but it's an important parameter also of the op amp. The input common mode range is an important parameter. Now, why is it important? Because sometimes you may want to use a single supply, but you still don't want to make any extra arrangements for biasing the input. In which case, let's say you design it so that VCMN is 0. Okay. If it is 0, you are operating with a single supply, but you can still have no extra biasing arrangement for the inputs. Okay. So that is why that input common mode range is of some interest. So it basically specifies what kind of circuits can drive this. Right? So let's take the amplifier we had. This is an amplifier of gain K, and here, this is again the classical picture of the op-amp amplifier. Okay. So what do I do to make it work with a single supply? The input here is measured with respect to ground, where ground is this point. Okay. And the output also appears between here and ground. So how do I operate this with a single supply? What do I have to do? What's that? So first of all I have to do is to this is the circuit, right? So this is the complete circuit. I don't have any implicit connections here. So then I remove the ground from this point and ground this. Okay. So now this will work exactly as before. What are the problems here? What are the problems you see? Huh? Which one? This one. This. Which node is not available? That's it. So V0 is not with respect to ground. Okay. So you will have to subtract the bias. And also Vin, typically it is driven from another circuit. It's not a floating voltage source that you can connect anywhere. Okay. So that is also Vin is available with respect to ground. Okay. So what do you have to do? So let's say the previous stage has a certain bias value, and on top of that it has a certain voltage. Okay, this V1 is what we want to feed to our circuit. Okay, and this is our circuit, and our circuit likes its input here. Okay, and also provides its output between the output terminal of the op amp and this point. Okay, and this is what we call ground. So what do I do now? So just think about whatever I described before, that first of all, the input bias does not have to be the midpoint of the supplies. As long as it's within the permissible range, it's okay. And the output bias, the output of this op amp will also have a bias, but then we'll have to remove it if needed using a capacitor, or just somehow make some other arrangement to subtract the bias. Okay. But first, how do we connect the input to this? So this is available with respect to ground. Okay. with respect to ground, that is, it's the same ground. We have V bias plus V1. And V1 should appear as the input to this amplifier. Add? Okay, which is V bias? Yeah. So what we have to do is we connect V bias here at this point, or this one. This one. So we had some supply voltages. So you're saying you remove this from this point? No, but then I have changed the performance of the op amp, right? Because before the swing limit was something, now it may be different. Okay. See, if I go back here, now when I had the ground, at this point, the op amp could swing all the way to V sub and to minus V sub, right? Approximately. So now if I change the value of the supply, I will change the swing limit. Let's say I don't want to do that. What's that? No, first of all, V1 may not be an AC signal. It could be a DC increment above a bias. Okay. I don't want AC coupling either, because I want the DC value of V1 to be applied to the amplifier. Okay. Huh? What's that? To do what? No, but no, let's not change the circuit, right? Meaning I want the same signal processing functionality. How would I arrange things so that V1 appears at the input and it behaves more or less the same? No, I don't want to do that, right? I don't want to change the total supply to the op amp. What do I have to do? So I already said that the input bias doesn't have to be the midpoint of the supplies. Okay. So you make this, you break this connection. Connect this to V bias. Okay. Then how do you connect the first stage to the second stage? First stage to our amplifier. You already done the job, right? Yeah. Yeah. So that's all you have to do, right? Is this okay or no? So now the input common mode of this is what? V bias. Strictly speaking, it's V bias plus V1 by 2, but we'll say the bias voltage is V bias. Okay? And what is the output I get? In terms of the input signal V1 and any other quantity of interest. Huh? So the output is V bias plus K times V1. Okay? So this in fact behaves like this one, right? It has its output around a bias value of V bias. So when you have to connect it to the next stage, you have to do something similar. Okay? So the reason I am going through this whole thing is still there will be, like when you have to simulate circuits and so on, there will be some confusion about what the ground is and things like that. When you see a classic op amp circuit, this is all you see. Or let's say we take an inverting amplifier. This is all that's there. Now this schematic will more or less work if you do have dual supplies. Then fine, this is ground and that is ground and everything works. But if you have a single supply, what do you do? There is nothing fundamentally complicated here. It's just a matter of adjusting the bias voltages. Now, I said that the behavior of the op-amp will not depend on what the input bias value is, okay, what the input common mode voltage is. So, I want a certain characteristics, I want a certain set of characteristics between the differential input VID and the output. Now, the absolute values of the inputs will be some common mode voltage plus VID by 2 and some common mode voltage minus VID by 2. So, the relationship between VID and V0 should not depend on the VCM. Okay, VCM you should be able to connect it to any, you should be able to have any value of VCM. The relationship between the differential input and the output should remain the same. Okay, that is the common mode input value doesn't matter. Now, of course, there are some limits to it. That is, you can't take it beyond the supplies and so on, but within its limits, it should not have much effect. So, that concept is known as common mode rejection. Okay. So, the input biased at VCM. When I say biased at VCM, meaning whatever the input differential is, on one terminal you see this bias plus half of that, and on the other terminal you see this bias minus half of that. Okay. And the characteristics of the op-amp, that is V0 versus VID, or the transfer function V0 divided by VID, should not depend on VCM. And in many cases, you see that VCM is not just a DC value, but it can have time varying components. Even then, it should have minimal effect on the output of the op-amp. The output of the op-amp should be predominantly governed by the differential input, not the common mode input. Okay. This idea is known as common mode rejection, and it's actually one of the most important things about an op-amp. Okay, so this common mode rejection is a very important concept. We'll quantify this more as we go along, and when we design the op-amp, we see what the common mode rejection is. Okay, but the basic idea is that the op-amp should not respond to the average value of the inputs. It should respond to only the difference value of the inputs. Okay. So, is it clear how to work with single supply op-amps? So, when you simulate and so on, this is what you do. Okay. So, everything that we do will be with a single supply. We will not use dual supplies, and this is how you can arrange your things. Okay. Any questions on any of this? Now, you can also use this if you are in a lab and you want to operate or you want to design some circuit with a single supply, then you can use op-amps perfectly well. You just have to provide the appropriate bias voltages to the input and it will work. Okay. You look up the data sheet to see what the permissible range of input common mode voltage is. As long as you bias it within that, it should work.
Sir, is it always possible to connect the input to the appropriate voltage that is device?
Meaning, what is the?
Means the op-amp don't have any restriction on the result value of device.
No, that's what. It has this hard restriction that it will be some specified range. Okay, maybe it is between, with a 1.8 volt supply, it could be between, let's say, plus 0.1 volt and plus 1.5 volts or something. But within that range,
if device is very small, that op-amp cannot make it as the common mode is equal to.
If the V-bias is very small?
Means very small compared to the desired value of the input common mode of the op-amp.
No, V-bias is something you choose. Okay. So, if you have an op-amp with a certain common mode range, then you have to choose the V-bias within that range. Or I didn't understand your question, I think.
Means, sir, we are having the V-bias from the another circuit.
Yeah.
This we don't have any restriction.
Well, so, okay, the question is if the bias voltage provided by whatever is driving our amplifier is incompatible with our op-amp. Now in that case you can't drive it. That's the only answer, right? So if you have a circuit which has a V bias value of 1.8 volts, but the maximum common mode voltage of your amplifier is 1.5 volts, then that means that you can't connect that amplifier to this amplifier directly. You may have to make some intermediate arrangement. So you have to change one of the two circuits, right? Okay, so that's the answer. So if it so happens that the bias value that you are getting out from your other designs or somebody else's designs is incompatible with your op-amp, then you have to either change your op-amp design or place a level shifter between the two or something of the sort. Okay. So this circuit operates from a single supply. It amplifies the difference between the voltage on this node and V bias, which is basically the desired signal. And the output is also riding on top of V bias. Okay. So you have to choose the right common mode and then bias your op-amp accordingly. What are the other non-idealities we may have? Offset voltage. So I said that it should be a straight line. In reality, it will go up to infinity. I mean, in an ideal case, it will go up to infinity. But in reality, it will be limited to something that depends on the supply voltage that you use. Okay. So the other non-ideality, as I mentioned, is offset voltage. What does offset voltage mean? Huh? So if you apply zero differential input, the output voltage will not be zero, or output. This again you have to be a bit careful that we are operating with a single supply. So the zero of the y-axis is not here, right? It will be. So in the ideal case, the output will be some it should be something. Let's say I'll call it V naught ideal. Okay. So in case of single supply, there is no question of output being at zero, right? It will be always between 0 and some upper limit. Okay, that depends on the supply voltage. Now, offset voltage means basically a horizontal shift in this characteristic. Okay. So the characteristic can look like this, or it can look something like this. Now, one thing about these plots that I am drawing is that the slope is maybe the slope of the line I have drawn is something like 5 or something like that. But with an op-amp, you need a very large DC gain. The slope will be like maybe 1,000 or 10,000 or something of the sort. So the line will be almost a vertical line if you plot it on equal with the equal scales on the x and y axis. Okay. So what is the problem with the offset? Okay, I have an offset. So what's the issue? So this means a horizontal shift, and if the slope of the line is very high, you can see that a small amount of horizontal shift will make V naught equal to either the upper saturation limit or the lower saturation limit. So what's the problem then? It is? Yeah. That's not. No, that's okay. But like, what happens if I am operating around this point? It's not behaving like an amplifier. See, I wanted a certain characteristic from the op-amp, certain transfer function. That was a high DC gain, and the high DC gain is in this range. Okay. So now I know that every circuit in reality is not linear, right? I only approximate it by linear systems. So I have to bias it somewhere within this range for it to provide high DC gain. Okay. So in fact, if it is biased somewhere here, it is clearly not an op-amp. It's useless for use in a negative feedback system. So how do we get around this problem? So the idea now is, let's say, one thing I could have potentially done is to apply some signal here, okay, and then expect that the output will be an integral of the input. That is, it's an integrated response or whatever the transfer function of the op-amp is. Now I know that I can't do this because if I apply 0 volts between the differential inputs, I will get, the op-amp can be biased anywhere. It could be biased here, it could be biased here. Now this horizontal shift is also random. If you buy some 10,000 op-amps and measure the characteristics, they will all be shifted by different amounts within a certain range. So how do we get around this problem? But how much? First of all, you don't know that the input, the extra voltage is negative or positive because the shift can be in either direction. Right? So what works for some case will not work for another case. So you have to somehow, without knowing the offset voltage, apply the right value of bias to the input so that the op-amp works in somewhere in this region. How do you do that? No. So you don't know what the offset is, right? And you don't want to make, if you are producing millions, maybe you have a very profitable company that's selling millions of things. You can't go with a potentiometer on millions of, maybe that will provide job opportunities to a lot of people, but somehow it's not an accepted, it's not an accepted business model, okay? What do you have to do? What is it that I want to control? I want to have the output somewhere here and I want to automatically adjust the input value. So what do? Negative feedback. Okay? So I use negative feedback for biasing also. I have to do this, right? Because I don't know what the shift is going to be. It is some random offset. So I just have to find the correct value of bias which will make the circuit operate in this. Okay, that is, I want to operate at, let's say V0 equals certain quiescent value, V0Q. Okay, so what do I have to do? So let's talk only about biasing. Let's not worry about what other processing the op-amp has to do. Okay, we have this op-amp. I want to bias this at V0 equals a certain value. Okay, so what do I do? And someone said negative feedback. Yeah, that's the right answer. We have to use it. But how? What's the idea behind negative feedback? If I want the output to be equal to certain value, what do I do? So we have to make this comparison, right? We take the actual output and we have the desired output. Okay? And then so I have to somehow feed this information back to the inputs. Okay. Now, when we started off with a negative feedback amplifier, we said we'll integrate the difference and then feed it back. Now, we already have an op-amp which does the integration, so we don't have to make another amplifier just for biasing. Okay. We just have to provide something proportional to this difference to the inputs. Okay. So the input VID should have what form should it be? what should be its dependence on V0 and V0Q? So it should be some constant, let's say K1 times V0Q minus V0, right? We want negative feedback, okay? And it doesn't have to be even a linear function. It has to have if you plot VID versus V0, it should have negative slope. The slope doesn't have to be constant also, okay? So this is the general thing. I mean, this is again something that you all know, and it happens in all op-amp circuits. But this should happen at DC, right? So when we were making different signal processing blocks with the op-amp, we didn't really say anything about a particular frequency. Whatever transfer function we want, we can realize by appropriately adjusting the feedback circuit. But this is something else entirely. This is because the op-amp is not biased correctly without DC negative feedback. Whatever circuit you make must provide DC negative feedback around every op-amp. Okay. On top of that, you can use, so once there is DC negative feedback around the op-amp, it will be operating with the right quiescent voltage at the output. Then you can use that op-amp as a virtual short or basically a high gain amplifier and realize any other signal processing function. Okay. So you have feedback around the op-amp to get the desired signal processing function, but for the op-amp to behave like an op-amp, I mean for a real op-amp to behave roughly like an ideal op-amp, you need to have DC negative feedback also. Okay? So whatever feedback network you put to realize your signal processing function must also provide DC negative feedback around the op-amp so that it gets biased decently. Okay? Is this okay? So let's go back and see if our circuit does indeed do that. We had a circuit like this, right? V bias V in. Now I want to evaluate if there is DC negative feedback around this op-amp. How do I do that? First of all, I ground the input. I am not interested in how it behaves for input signals. That's a separate analysis. Okay. I just want to make sure that the input voltage at DC is somehow related to the output so that we get negative feedback. So what is VID as a function of V0? Huh? What's that? Minus V0. So VID is minus V0 by K plus V bias. That's it. Is this correct? So we have VID equal to this one. So what value of what will be the quiescent output voltage V0? What will be the quiescent output value of V0? Huh? Yeah. So okay, what is it? V bias times K minus 1. Okay. So, but previously we said that the output gets output bias is V bias. What is wrong with this? It is V bias. The output value is V bias from this equation. Yeah, that's correct. VO with respect to ground is what? How do you find out the output quiescent value in this case? Huh? V bias times K plus 1. See, when it is working properly, the input quiescent value should be very small. So in that case, the output will be V bias times K minus 1. Okay? But is this what we wanted? What is wrong with this whole picture? What's that? V bias is getting amplified. See, what we said before was that the input voltage is around a value V bias. Okay, so the quiescent value should be evaluated with a quiescent value of V in. Okay, so what is the quiescent value of the input? V bias. Okay, so what is VID? Huh? Yeah. So, first of all, I think this whole thing was wrong to start with. It was minus this one, right? So the VID in this case is V bias minus V naught by K plus V bias K minus 1 by K, which is what? Okay. So the output does go and get biased at when VID is small, the output will get biased at V bias. Okay. So we'll continue this. I think the last part looked like it was not very well understood, but we'll continue this in the next class. But the bottom line is that every op amp needs to have DC negative feedback around it. Okay. So if you have a circuit with multiple op amps, you have to work out that every op amp has DC negative feedback around it. The negative feedback path can be through passive components, can be through active components, but whatever it is, for DC, you have to have negative feedback. Okay.